In linear second order differential equations, especially when you have a homogeneous equations, the method of reduction of order is used when you know one of the solutions of the equations, not everywhere near zero, of these equations, second order linear homogeneous differential equations here. So again, you have a differential equation in this form, and you know one of the solutions y1, then you can find the second solutions and use the Kronskeian value in order to determine whether the first solution and the second solution that you just found form a fundamental set of solutions. All right. Well, the setting is first you need to convert, or you need to make sure that your differential equation in this correct form. You have y double prime plus b of t y prime plus c of t y equals to 0. Then you know one of the solutions y1, and then you find the second solution y2 by the guess that y2 equals to v of t times y1, where v of t is the unknown functions, which we're gonna find, okay? So if we set y2 equals to v of t times y1, then I can find y2 prime. And y2 prime is v prime v1 plus v y1 prime, right? And then I can find y2 double prime, which is equals to v double prime y1 plus v prime y1 prime plus v prime y1 prime plus v y1 double prime. Okay, and from here, since this and this are the same, I want to combine them together to make it 2, but v prime y1 prime. All right, now I have y2 prime and y2 double prime. I can plug y2 of this information into the original equation because I assume that this is the solution. Okay, by plugging it in, I would have y2, oh, this is v y1 double prime. So y2 double prime is v double prime y1 plus 2v prime y1 prime plus v y1 double prime. And then I add to b of t, right, of y2 prime. And y2 prime, I found it in here, is v prime y1 plus v y1 prime. And then I add to c of t of y2, which is just v and y1 equals to 0. Keep in mind that because y1 is a solution to the differential equation, so then this equation will be true. All right, so let's simplify this equation. We have v prime, right? V double prime, this is only one, so I cannot group it with anyone else, so I just keep it at this. So v prime y1 prime, there's no other like terms, so I just rewrite it. y1 double prime, I don't have anything else to group it together yet, so I just rewrite it, but then I can distribute the b of t into this bracket. So I have bt v prime y1 plus b of t v y1 prime, okay, plus c of t of v y1 equals to 0. Now let's see, I have v, I have v here, so they are common terms, so I can group them together. I can group these 3 terms together, and the rest of the term I just rewrite them for now. So I have v y1 plus 2 v prime y1 prime plus b of t v prime y1, right? And plus, now I group v, and I have y1 double prime plus b of t y1 prime plus c of t y1 equals to 0. Now that you can see that this is the original equation in terms of y1. So I know that this is going to be 0. If this is 0, then this is the only terms left over, right? So I just rewrite them. Say v double prime y1 plus 2 v prime y1 prime. And I have v prime and v prime are the common term, so I can just factor it out for now. Factor it out, I have 2 y1 prime plus b of t y1 equals to 0. Now we have a second order differential equations. The constant are not, the coefficients are not constants. So we haven't learned how to solve this equation yet. But because in this equation, there's only v double prime and v prime, there's no v, then we can think of reducing this differential equation from the second order down to the first order by introducing a new variable, w equals to v prime. If w equals to v prime, that means w prime equals to v double prime. As you can see that I am reducing the order of v double prime into w prime, right? And I can replace v double prime by w prime. So you have w prime y1 plus w2 y1 prime plus b of t times y1 equals to 0. Now we have first order differential equations, and lucky enough, we know how to solve for the first order differential equation if it's linear. Okay, and this is linear equation. So the next step is I can solve for w. Okay, you can use either separable equations or integrating factor. Okay. Well, once you solve for w, remember that we let w equals to v prime, and the goal is again start solving for v by integrating w. Okay, in terms of t. So you're integrating w, you get v. Okay. And once you have v, then you can multiply, find y2 by taking y2 equals to v times y1. Okay. Because remember, we know y1, we assume that y2 equals to v times y1, and now we can find v, then we can find y2. And then the last step is find the Kronskeian of y1 and y2 to determine. Okay, so if the Kronskeian value is different than 0, then y1 and y2 form a fundamental set of solutions for the differential equations. Otherwise, it's not. Okay. So these are steps that you can use in order to solve for the second linear order differential equations, homogeneous equations, using the method of reduction of order. Okay. So let's summarize all the steps. First, you let w equals v prime, plug it in this equation, solve for w, integrate w to get v, multiply v by y1 to get y2, right? And check using Kronskeian to check whether y1 and y2 forms a fundamental set of solutions for the equation. Well, let's take a look at an example. First example here. So in this example, the first thing you always want to do is you want to transform the equations into the correct form, right? So I have to take everything divided by 2t squared. So I have 2t squared y double prime divided by 2t squared plus 3t y prime 2t squared minus y over 2t squared. Okay, equals to 0. And from y1, remember that we want to find y2 equals to v times y1, okay? And then the next step is to be sure I want to identify, and I want to simplify this, right? So it's y double prime plus 3/2t y prime minus 1/2t squared y equals to 0. And then this is my b of t, and this is my c of t. Better. All right. So again, the next step is let w equals to v prime, right? Then w prime equals to v double prime. And then I want to consider the equations in terms of w. The equation is y1 w prime, y1, and y1 is 1/t, so 1/t w prime plus 2y1 prime. And what is y1 prime? If y1 is 1/t, then y1 prime is going to be negative 1/t squared. So 2 times negative 1/t squared plus b of t. B of t is 3/2t times 2y1, which is 1/t. Okay. Multiply to w equals to 0. And now we go to solve for w using separable equation or integrating factor. Before doing that, I want to simplify this first. So I have 1/t w. This is t squared. This is 2t squared. So I have to multiply by 2 here to get 2t squared. And you have 4 minus 3 should be 1. So plus, it's negative 4 plus 3 should be negative 1 minus 1/2t squared equals to 0. So I'm going to use separable equation to solve for w. I would have 1/t w prime equals to 1/2t squared w. Okay, so then I would have w prime over w equals to t over 2t, so 1/2, 1/2 times 1/t. And then I want to integrate both sides, right? I got dt here and I got dw here. Okay. Well, then the next step is again just finding this integrations, which is natural log of w equals to, say, 1/2 natural log of t, right? Plus c. Okay, well then that means w equals to t raised to 1/2. And you have t raised to 1/2 here. And in this case, I'm gonna keep the c, and you know that it's gonna be c1 t raised to 1/2, right? So this is w. So once I found w, I can go ahead and try to find v. So that's the next step. So next step is find v by integrating. So v equals to integrate of c1 t to the 1/2 dt. And that's gonna give me so it's gonna be c1, right, t to the 3/2 over 3/2 plus c, okay? And if I want to simplify it, I would it's just gonna be 2/3 c1 t of 3 over 2 plus c2. Well, let's give it another constants. All right, so I have v, then, oh, I'm almost there, right? Now I need to find y2, and y2 I know that it's going to be v times y1, or y1 times v equals to 1 over t times 2 over 3 c1 t of 3 over 2 plus c2. And I can simplify and distribute it out, simplify it, and I have 2 over 3 c1 1 over t times 1 over t, and it's t of, so if I distribute this in here, you will get 3 over 2 minus 1, so it's just t 1/2 plus c2 1 over t, right? So this is y2 that I found, but keep in mind that, and I know in the fact that I can just ignore the c2 here because c2 1 over t, it's just y1. So it's repeating this root, so I can ignore it. And the constants here, I can just ignore the constant for now because I just want to extract these functions out of this y2. So you can ignore, because it's just y1, and then y2 here will be just t raised to 1/2. Does that make sense? This because I ignore this because it's just y1. You add to y1, you're not gonna, it's the same as doing a linear combinations, right? And then you want to like find the y2 that is independent from y1. So I ignore this and I just extract this and ignore the constant for now. And then the last step is I want to find the Kronskeian of y1 and y2. So y1 is 1 over t, and y2 is t to 1/2. Okay, then y1 prime is negative t to the negative 2, and y2 prime is going to be 1/2 t to the negative 1/2. All right, remember how to find the Kronskeian. You do cross multiplications here. So it's going to be, okay, I'm just going to separate this. Okay, so it's going to be 1 over t times 1/2 t to the negative 1/2, right, minus negative t to the negative 2 times t 1 over 2. Okay, well, I'm going to have 1/2 t of negative 3 over 2 plus t over negative 3 over 2, then you will have 3 over 2 t to the negative 3 over 2 is a Kronskeian of y1 and y2. And in this problem, the domain of t will be positive. Since t is to be positive, then the Kronskeian of y1 and y2 will be different than 0 for all t. That means y1 and y2 that we just found forms a fundamental set of solutions for this differential equations. Okay. All right, so this is the method of reduction of order if you have a second linear differential equations, homogeneous equations, and if you know one of the solutions, you can use this method. in order to find the second solutions. And to just make sure that the two solutions form a fundamental set of solutions, you want to use the Kronskeian to double check the answer. Here we go. How you find the second solutions of the second order differential equations. So first, let W, call out a variable W and put W into this differential equation here. Solve for W, integrate W to get V, multiply V by Y1 to get Y2. All right, here you go. Method of reduction of order.